So let me do this to give myself a moment. You guys, go ahead and take a minute and figure these out. What is the GCF of 480 and 100? You can do it, Jeff. 36, I like it. And what's the LCM of, what are you gonna do, buddy? I don't know. 18 and 28, I like it. So take just a couple minutes, try to do that.
Okay, what?
That was great. Okay, I think that's ready. All right, so who's got, now, like on a test or a quiz, I could ask for a specific method. Did anybody use a specific method on the first one? Or what did you guys do? You must have, it's kind of a silly question. You're all like, yeah, we did something. So that's a method, Jeff. What did you guys do? Anybody think they got that answer for the first one? Okay, I see pained expressions. All right. So one method that we could use, we could do silly things. We could try to write all the factors and just kind of see what the biggest one is, right, for each. And that, in this case, would be silly. Those are kind of big numbers. 480's got a billion ways, roughly, to factor it, right? So I don't want to do that way. What's another way I could figure out the greatest common factor? Huh?
The division thing.
Division thing, right? Which is, and there's an intermediate step. There's the subtraction thing. And then, of course, division is just repeated subtraction. So that's why it kind of lends itself to the division approach. I like it. You guys all with me? So one little mantra you're going to have when you're teaching certain levels of of school is multiplication is repeated addition, division is repeated subtraction. It's a beautiful analogy. Okay. So if I do the division thing, what do I get?
Remainder 72.
Yeah, so you get 3, and that'll be, what is that, Jeff? 309 is 100, no, 300, 408? Okay, there we go, that's how you get 72. What's the most important thing that just happened there? It's a weird question, I know, I'm sorry. You're all like, I don't know what you want from me. What is the answer that's gonna tell me what to do next? What piece of that division problem? Is 3 important?
No,
Nope, 3 didn't matter. We're shit. I just did 3 of these. So what matters is what's left. So if I subtract 136 from 480 3 times, I would be left with the 72. That's sort of like an entirely kind of different way to look at division, right? So now, what does this equal? This. What does that equal? The GCF of?
72.
Yeah, so I can replace the big dude because I just subtracted him down to a smaller place. I like it. So that, whatever the GCF is of these two, it has to be the same as the GCF of 72 and 136. And now I can just kind of go for subtraction because division's not going to help out a lot. So 136 minus 72 is 64. I like it. So now it's a GCF of 72 and 64. And then we'll be basically there in a minute if we're not there already. Because if I do one more subtraction, 72 minus 64 is 8. So what is the GCF of 8 and 64? What's the biggest number that goes into both 8 and 64? 8. Kick ass. So you don't have to take it all the way down until you get to like a number in itself or something. You just need to get the numbers down to a place where your brain goes, okay, I can see that. I can't see this. Screw this. I don't know. 2? I don't know. And then you get there, okay, 8. I can see it. The numbers are smaller. I can deal with that. How's that? Is that all right? That's effectively the ultimate place we got to, kind of the final form of finding this GCF by hand, right? Yes?
I know you probably said this before, but what method was this again?
So the intermediate steps for finding GCF, the first thing we did was set intersection method, which would be, how would that look for this? It would be list all the factors of 480, list all the factors of 136, and then see what's the biggest one. So the bigger these numbers are, the more foolish that approach is, right? So for little ones and you're dealing with like 12 and 15, that is not a very big list, right? Okay, I like it. And you want to reinforce just the idea of making lists of factors anyway. So it makes sense to do that as a practice anyway, right? When we get to this level, I need something to help me out, and we developed the theorem that says if I subtract these two, the greatest common factor of what I get when I subtract should be the same as the greatest common factor of what I had to begin with. And that was built off of that whole thing I said about if two numbers have a factor in common, they have to exist on the same kind of like multiple, like 3, 6, 9, 12, so forth. So subtracting between two numbers sort of leads to that idea being used, that they have the same factor in both. And of course, subtraction leads to division. If I want to subtract something multiple times, it's a shortcut. I like it. Is that all right? So does it have a name? No. It's just the process to find the GCF. All right. How you guys doing? Okay, what about LCM? What?
Like the little equation kind of approach, like the A times B over the GCF.
Oh, okay, sure. So one, that's awesome. You went straight to the final form. So what is the GCF of 18 and 28? They're relatively small numbers, so 2. Therefore, the LCM of 18 and 28 has to be, I don't know if you guys remember this, but it's got to be 18 times 28 divided by 2. And again, last time we talked about why this makes sense. What is it? 252. All right. I like it. Now, if I didn't go all the way to that final form, what's a step before that I could try to do? What method do we have to find the LCM? I mean, the very first method, again, is sort of a silly one. You just start writing multiples of 18, and you write multiples of 28, and you see where do they meet. In this case, I know I'd have to go all the freaking way out to 252, so. Right? Did we have another method to find the LCM besides that? Yes, so prime factorization. So, is this all coming back? Are you guys with me? Okay. So, and again, on a test or quiz or something, I would say use this approach. Use the prime factorization approach. Use the set intersection approach. You just have to remember what those reference, right? What's the process for each of those? If I break 18 down, I'll get 9 times 2, so I get 2 times 3 squared. Is that cool? Break 28 down, I get 4 times 7 to 2 squared times 7. It's always this room. I don't know what it is. So, you can go back to it's always great. The idea of ice cream, I love that idea of like, the two kids are not going to be happy if one's got sprinkles and one doesn't. That's obviously going to lead to a lot of problems, right? So, what is he missing that he's got? So if I write one kind of direct approach is just write one of them down. The LCM has to have both of those in it. So you just start with one of them. Now start giving it what it's missing compared to the other one. So what's it missing compared to this guy? This guy's got how many 2s? 2. He's only got 1. I'm going to give him another 2. And of course this guy's also got a 7. So then the answer should be 4 times 9 times 7. And I want you to notice something. 4 times 7 is 28 times 9. Of course, that's still 252, right? Okay, so either way, you get to 252. I love it. You guys sort of with me? Okay, I use this one all the time. The way you told me at first, the GCF approach. Yeah, so when I'm teaching factoring, I try to show students that on the side, because, or even when I'm just teaching adding fractions. So we're about to get into fractions, so I feel completely fine doing this to you. If you didn't realize we're about to get into fractions, we're about to get into fractions. So, okay. Some of you guys do not, I like how you put your feelings completely out there. This is relatively easy. Does anyone completely disagree with me? Why is this? It's not as easy as it could be. If I made that 4 and that 4, that would be the ultimate easy, right? This is the next level of easy because there's very little thought. Do 4 and 5 have anything in common? Do 4 and 5 have any factors in common? 4 and 5, do they have any factors in common? 5 is 1 times 5, 4 is 2 times 2, or 1 times 4, they have nothing in common. So they need each other, right? So this guy needs a 5. So in this case, what did I call these? Their relationship? Neither one of them is prime, but they are relatively prime. Relatively prime kicks ass. So this approach, remember, it's the product times the GCF. I'm sorry, divided by the GCF. Isn't the GCF 1? So isn't it just going to be the product? Are you guys at all with me? This guy needs a 5. This guy needs a 4. I don't have to think barely at all. Just give them each what the other one is. The minute I make this 1/4 plus 1/6, 4 times 6 is not the LCD. But now I can use that approach. It would be 4 times 6 divided by what's the GCF? 2. All right, so 12 would be the LCD, right? So that's kind of like the place I at least used to teach it back when it was legal for me to teach that. That was one of my favorite classes with Math 80. I loved the shit out of that class because, I don't know, you get these students and you can kind of, it's like these huge insights suddenly of things that they've been working with their whole life, and they're like, I finally understand that. Now, do I get that with every student? No. But, with most students, yes. Anyway, sorry. Okay. That is an immediate place to use the idea we just applied. And again, LCM is just another name for LCD. We just call it LCD when it's a denominator. Okay. Is that everybody with me on that? Okay, so let's do this. Let's watch a couple of videos of little ones trying this stuff out. What you guys think about fractions already. Can somebody give me like an actual real life place where you might come across a fraction? Do you ever come across a fraction in real life? Yeah. Change, okay. Yeah. Baking, totally, right? It always gets exciting when you're like, oh, I need to get 3.5 times this, and you're like, oh shit, this is, oh my god. And then you just sort of maybe try to feel out, and then it doesn't come out well. Baking is awesome. Baking is a perfect place. Change, I can see that. Anything else? Measurement, so almost any measurement you take, right? So you can get 1/4 of an inch or something. If you're trying to put something up and you're trying to figure out how far apart the studs are on the wall, it might come out to be some fractional part of an inch, right? Okay, cool. So fractions show up everywhere, right? To me, one of the big places is like you drive around gas tank. You have one full gas tank, and then you got like it could be half full, 1/4 full, so forth, right? Okay. I think where students have the most trouble with fractions is just number one, just understanding what they by themselves even mean. So it makes sense to us to say, I'm going to take half of that cake home, right? If I say that, that makes sense because we're not even thinking about them in any kind of math sense. Cut the damn thing in half and take it home, right? We don't think about the number 1/2 as a number necessarily. We think of it as a word that describes I'm taking half of that sucker, right? So what do you think you would use to show a student what a fraction is? Like, we've sort of done similar things to this before. So you can start with talking to students to say, okay, give them like 8 pieces and say, now separate that in halves. And they normally will be able to do it. They kind of understand the word half, what it means. But 1/2 by itself has meaning. It's a number on its own right? The very first place we try to build up a feeling for what fractions mean is to not look at them as their own numbers. We look at them as meaning half of something. And one of the first ways you want to teach students anything is very visually, right? So for example, if I had this, right, to represent 1/2, I could just shade in half of the sucker. Now, the funny thing is, the immediate thing you can do on top of this, so I've taken one box, let's say, and I cut it in half. So of course, if I shade that, one of the 2 pieces I just created, that is 1/2 of a whole box, right? That's round shape. What does it mean if I then do this? Now how many little boxes are filled in? Out of how many? Yeah, so this is now 2/4, right? And that's kind of like the first step you can take to having students understand what equivalent fractions are. 2/4 represents the exact amount, same amount as 1/2 does. So that's why 1/2 equals 2/4. I like it. Now, real quick, I want you to realize something. There are multiple, in fact, there's an infinite number of ways to represent 1/2, because I can just multiply top and bottom by any damn whole number, right, except 0. There's the same thing for like a whole number. How can I represent 8? How can I represent the whole number 8?
8 circles.
Okay, 8 circles. I could also represent it as 4 groups of 2 circles, correct? right? And this is kind of going back to the idea of multiplication. Are you guys kind of with me? I could also represent it as 2 groups of 4 circles. That's amazing. I could represent it as 1 group of 8 circles, right? I could also represent it as half of a group of 16 circles. Okay, maybe. So the fact that there's multiple ways to write the same fraction, there's also multiple ways to write the same whole number. Okay, I like it. So the way we normally do fractions to begin with is this very visual method. And this is called that is called a dead marker, poor little blue. It's called a region model. Believe it or not. All a region model is you pick a shape, you cut it up into equal parts, and you shade some of those parts, right? So let me ask you to do this for me. Can you all just, well actually let me do this. Another way I could represent 2/4 would be take a circle, cut it up into 4 parts, and then shade 2 of those parts. That's astounding. I could also represent 2/4 as this. This is basically what I was just saying earlier a little bit. A complete set would be 4, so if I shade 2 of them in, I've shaded 2/4 of a complete set. Does that make sense? Okay, I like it. So can you guys real quick just, can you draw a region model to represent 3/8? Purple, you're my only hope. Let's see. All right, so what shape did somebody pick? So many possibilities. How did, circle? Circle. And how did you get it cut up?
First 4th,
I like it.
and then 4 more, or 2 more rounds.
Yeah.
Yeah.
Pretend like that's good. Okay. And then of course you just shade it in 3. That's crazy. Whatever 3 you want. Okay. So again, this would be, normally kids totally understand pizza, right? So pizzas are obviously really good for fractions because you can cut a pizza up into whatever many slices you want. Just about? Okay. All right, nothing amazing there. Region model, you've all seen this kind of thing before about fractions. One thing I want you to realize, here's something kind of weird. The number 8. So, for example, 8 chairs. Okay, great. So 8 could represent a certain number of items. But just the number 8 by itself, isn't it 8 ones? 1 plus 1 plus 1, we decided to call it 8. If I have 8 of them, right? So every whole number is counting a certain number of ones. Again, very ground shaking. If instead, so all fractions do on one level is this. They say, okay, instead of counting ones, what if we count 4ths instead, right? So instead of counting ones, let's count 4ths instead. So if I'm here, I've got 1/4, right? It's incredible. So on one level, it's not really arbitrary. It naturally makes sense to start counting one whole thing, another whole thing, another whole thing. But there's nothing preventing us from counting 1/4 of a thing, right? So of course, if I'm counting by 4ths, how many do I need to get before I get a full 1? 4 of them. Okay, I love it. So one thing I was imagining was, what if there's a Lego set? Legos. Anybody play with Legos when they were little, or still to this day? I don't know. You can get some crazy ass Legos going on, but let's say there's a Lego set, and the first thing you have to do to construct this thing is to put together 3 pieces and it makes a little part, right? So it takes 3 Legos to make 1 part. And then the parts you can kind of stick together. Are you guys kind of seeing where I'm going with this? So each little Lego is of course how much of a part. So another way to think of fractions is kind of keeping track. I need 3 total. I've got 1 out of 3 of the things I need, right? And again, you could actually bring in freaking Legos. You can have the little parts, right? You can put them together. So if I say, oh, look, you only got 1. How many you're missing? I'm missing 2. So you got 1 out of 3. So 1 Lego would be 1/3 of a part. So this is sort of a concrete way of what I was just trying to explain with the whole 1 versus 1/4. I can count in terms of parts for this example, or I can count in terms of Legos. 1 part is 3 Legos. Therefore, 1 Lego must be 1/3 of a part. Are you guys at all with me on this? Okay. All right. That came out of nowhere. I didn't even think about doing that. Okay. So just to formalize things a little bit, and I think we talked about this already. Here's more earth-shattering stuff. So how would you define a fraction? Like if you had to really get down to brass tacks and define how to put together a fraction, right? I don't mean like what situation could a fraction represent? Just how would you explain to somebody how to construct a fraction? How do you construct one? How do you just put it together, right? What does it require, a fraction? It needs a numerator and a denominator. I like it. And those are actually based on, like numerator is numeration, to count, and denominator is based on nomenclature, which is to name. Just in case you're curious where the hell those came from, and then we can all forget. Right? So those actually come from places, and actually I'll come back to that again later. So it needs a top and a bottom. It needs a numerator and a denominator. What's got to be true about those? Right now we're still not considering negative numbers, but obviously fractions can be negative. What is the one absolute thing that you must say right now in order for this to not go crazy? What's got to be true?
The B has to be bigger than A.
No. What can B not be? What can you not divide by? 0. So that is the absolute most important thing here, right? And we did talk about division by 0, didn't we? I think I did my whole spiel about it's not defined to do what it's supposed to do. Okay. All right. And again, I kind of don't like this about this book, but again, I don't necessarily know how much this mirrors the way it's taught. I have something against completely ignoring negative numbers until later. So right now, the book is going to talk about A and B have to be positive, right? A could be 0, but B can't be 0, but they have to be positive. Okay, you guys all with me? But we know fractions can be negative. Okay. And I like what just came up about the situation between A and B. If B is greater than A, right? So give me an example of that. Give me a fraction where B is greater than A. Any fraction. 4 over 8, 11. So 4 over 8, that's the situation. Right? If A is less than B. So this is an example. What's an example of that? Anything. 11 over 8. 11, right? What do we call 11 over 8? We give it a special name. Improper. Do you guys remember that? That would be an improper fraction. We would also call it top heavy, right? Okay, maybe. Do you guys remember what you could do with that to put it in a different form? Okay, we'll get there. Coming back to the Legos real quick. I want to talk about what we just talked about. If I have 6 Legos, how many parts can I make? how many parts does it take, how many Legos does it take to make one part? 3. So if I have 6 Legos, how many parts can it make? 2. I love it. If I have 8 Legos, how many parts can it make? 2. But the difference here is, don't I have 2 left over? Right? And how do I write that? Well, if I have 2 Legos left over, how short is that to make a part? 1 short, right? So I have 2 out of the 3 parts I need. Stay with me. Okay. So what's weird for me real quick is I know that several of you guys have voiced opinions about fractions. And what I really want you to do is while we're discussing these, I want you to ask whatever the hell question has ever eluded you the answer to, right? If there's anything about fractions that you're like, why the shit does it do this? You don't have to say it like that, but you can say that idea, right? Why does it work like this? What does that mean? Ask away, right? How did you get 2 here? What was the shortcut to get 2 here? I had 6 Legos, so how did you get to 2? No, I'm sorry. 6 Legos. Why was the answer 2? What's the shortcut? How many Legos does it take to make one part? 3. So what do I do to 6 to get 2? 3 times 2 is 6, or 6 divided by 3 is 2, right? So what's another way to represent this then? 8 Legos divided by 3. So those must be equivalent. You guys see that? You guys see that? I divide how many Legos I have by 3. Physically, that would be grouping them into groups of 3, correct? So you could actually give a child and say, divide it by 3. You put it into groups of 3. So 8 put into groups of 3 does not come out to an even number of groups of 3, correct? And that again is kind of like where a fraction can come in. You have to have a fraction to represent how close is one group away from being a complete. So real quick about this improper fraction, the mixed number stuff. I don't know if you guys have ever seen this. So one way to do this is just a long divide. The way I like better is, what number just below 8 do you wish was up there? 6, right? Isn't this, so that's 6 plus 2 divided by 3, right? 6 divided by 3 is 2, and 2 divided by 3 is, I don't know. So that's a more direct way to get it to be a mixed number, right? That's basically what division does. It finds that excess. Remember when we had a remainder, it's just how much over the original number was from the bottom going evenly. So that's just a very direct way to just see it. Okay, now I want to say something about this. In algebra, when I have 2x, what operation is that understood to mean is happening between the 2 and the x? If I have 2x, they're multiplying. What does this mean? Adding. This is one of the most unfortunate decisions in all of math history, is to write a mixed number like this. How else would you write it? I don't know, but they could have brainstormed it a little bit further. Do you see how a student can very easily think this is 4/3? Because they see that it's 2 times 2/3. Are you guys kind of with me? And of course, that doesn't make any sense, because 4/3 is just over what? 4/3 is just a little bit more than 1. 2 and 2/3 is obviously more than 2. So those can't be the same number, right? So that could be something that you need to address. And again, it's just a poor choice of notation back in the day. Okay. So here's kind of a silly example of what we're talking about. Going back to pizzas. So let's say that I need 8 total. I need 8 pizzas. I need 8 pizzas. I just need 8 pizzas. And they come in packs of 2 for some reason, right? Like one box has 2 pizzas in it. So Each little box has 2 pizzas in it. Okay. So if I have if I only have 1 pack of pizzas, if that's all I have is this 1 pack, right? And how many total packs do I need? So I need 8 pizzas. So how many packs do I need? 4. So I need 4 packs, because they each have 2 in them, right? Okay. So how much out of 4 packs? I only have 1. So that would be 1 out of 4. In terms of pizzas, how many pizzas do I have? I have 2 and I want 8, so I have 2 out of 8 pizzas, and that's another reason why those are equivalent, right? Each pack has 2 pizzas in it, and that's why you could double the top and bottom and it still physically represents the same thing. And again, I understand, on one level this should be where we live pretty comfortably. I think all of you guys could take a fraction and build it up, right? So if I gave you 1/4 and I said make that over 12, what would that be? 3, okay, 3/12, right? So building this stuff up is pretty simple. But again, this is not something we're born with, right? So they're gonna have to understand why this makes sense. So there's almost too many ways to play around with physical representations of fractions. Okay. Oh, speaking of which, and if I recall, I don't know if we have these back there. We do have some manipulatives we're going to be playing with eventually. I will eventually shut up and you guys can play around with these little figures that represent fractional parts. The last time I looked, I don't think we had enough of these, but there's these things called fraction strips. Okay. So what do you think that first strip could represent? If I shaded some of that in, it could represent so many what's, fourths, right? And then another one would represent how many eighths. So we pretend like they're evenly spaced, okay? Give me a little board license. So if I do this, that would be the same as that, right? So that's a quick visual. That's a little fraction strip that exists. They could hold it. They could put it right next to another one. And that, what idea does this represent? Yeah, what would this be? 3/4, and this would be 6/8. I love it. So again, just reinforcing that idea that there's a ton of equivalent fractions, right? Now, of course, how do you capture this? Any fraction a over b, where a and b are whole numbers, b not equal to 0. Okay, so it's always in the background whenever I write a over b. They're whole numbers and b's not 0. How do you generally create an equivalent fraction? What do you do? How would you create an equivalent fraction? Yeah.
You could multiply the top and the bottom to make a new fraction.
Totally. By what? Multiply by what?
2.
You could do it by 2. You could do it by 3. So how do I represent it in general?
By the same number.
Yes, okay. So how would I represent that?
A times n.
I love it.
A times n.
I love it. Kick ass. Again, nothing ground shaking there, but from the perspective of somebody who's first learning this, that's kind of huge. Now, for us, I can see very quickly those are the same because the ends would just do what? Cancel back, right? And a student normally can pick up on that pretty well once they learn multiplication and division are opposites of each other. They can see that happen. But it helps explain, this visualization, and there's the math kind of happening behind it. Okay. And I love the book makes a point out of saying that this is equal to this. Yes, book. We have commutative property, no problem. Okay. So I don't think I've hit anything yet that's too freaky. I think most of the time the trouble students have is when we're trying to add, subtract, multiply, divide fractions, right? I do think that some of us don't really like just poor little fractions sitting there, like the fraction 11/17. Could you come up with, not a visual, but an actual problem that would illustrate 11/17? Not even a problem, it's just a situation that would illustrate 11 out of 17, 11/17. What you got? You're like, I just said I could, man.
17 total kids in a classroom and only 11 showed up today.
Good, all right, so a complete classroom would be 17 kids. And we're 11 out of 17 of the way, right? Kick ass. It's basically almost everything would sound a little bit like that. Yeah, okay. So, again, it's instead of counting by ones, like this is one block, we decide to count by 17ths. So 1/17, 2/17, until we get to a full block, it'd be 17/17. Okay, I like it. Now, so let's start getting into stuff that might get a little bit weirder. What is the most direct way to tell if two fractions are equal to each other? Right, so normally, for example, why is this really easy to see these are not equal to each other? Yeah, they're already simplified. And this is 4 parts out of 5, and this is 3 parts out of 4. Right, now, how could you show a student that these are not equal to each other? What would you do to show a student that these don't equal each other? What would you do? So I had some visuals earlier showing that something was equal to it. So if I use fraction strips, what would happen? So try to illustrate 4/5 and 3/4 with a fraction strip. I'll stand up here and look at you as you do that. Turn you back on yet? Try to make sure that the strip is the same size for each, sort of. It's weird at the board. Okay. Oh, real quick, while I'm thinking about this, because it's related, right? Because how many, remember that problem a while back? It just came to mind and nobody asked me about this. Remember the problem a while back where somebody was cutting so many pieces of wood? It was one of the bonus problems. And I don't know if anybody got that right. Maybe one person got it right. So a lot of you guys were like, if it takes 10 minutes, I don't know what I said, to cut a piece, how long would it take to cut 5 pieces? You wouldn't do anything with 5 because I would only have to cut 4 times, correct? So that's a mistake basically everybody made on the problem was, I don't have to do anything based on 5 because the minute I cut 4 cuts, I've got 5 pieces, correct? Okay, so I just gotta do 1, 2, 3, 4 cuts, and then I got 5 pieces. Here I gotta do 1, 2, 3 cuts, and I got 4 pieces, okay. So 4/5 would go this far, 3/4 would go only that far. So that's a really good visual of why those fractions are not equal. Because again, 3/4 and 4/5 are weird. A student's not going to be understanding immediately that those aren't equal. We can see that they're freaking not equal. If they were equal, they would be the same number, right? Okay, maybe. So the visual is really helpful. So then you can start to talk about the fact that in order for fractions to be equal, they have to, I think somebody said this earlier, they have to reduce to be the exact same thing, right? They have to reduce to the same ratio. So if I'm given a problem, and I want to know, is 12, you can do it, Jeff, 12/40 are 12/40ths, and you can do it, buddy. You can do it, Jeff. Let's see. 20/80. Sure. Are those equal? Yeah, why not? Yeah, the quick way to do that one, so this is, okay, good. I love it. So you could either tear them down or you can build them up, right? So I could reduce each one, or I could make this become 80. Okay. You guys kind of with me? So I could either, all I need is for the denominators to be the same, so then I can see how many of each part do I have, right? So I've got 12/40ths, but that translates into 24/80ths, so 80th. So that's obviously true that that one's bigger. So I could say, Chihuahua. Okay. But here's a nifty little thing. What if I wanted to know which one of these fractions was bigger? 15/31 versus, what you got, Jeff? You got something, there it is, 19/37. I wanna know if they're equal. They're obviously not equal, do you guys agree? Are they already reduced? Do those reduce anymore? All right, so I know they're not equal, but now I'm curious, which one's bigger, right? You're like, that's your problem, Jeff. Oh, no. How could you tell which one's bigger? It's kind of related to what we just did, right? So these are relatively prime, so I could just give each one the other one, right? So here's a bit of a shortcut. If I just cross multiply, now, what happens with a lot of algebra, students cross multiply too often. Do you guys know the one time you cross multiply in order to solve something? Do you guys know when that is? There's one time when cross multiplication is used to solve something. Do you guys know what that is? If I have like x/5 equals 3/4, then I can cross multiply, right? But students try to cross multiply in all these different situations. And cross multiplication is just a shortcut. But here, do you guys see, even here it's a shortcut. How would I make them have the same denominator? Wouldn't I just multiply this one by 37? And which part do I care about? If I multiply this by 37 and I multiply this by 31, will their bottoms be different? If I multiply this one by 37 on the top and bottom, and this one by 31, what will be true about the denominators? They'll be the same. They'll both be 31 times 37, correct? So don't I only care about the tops then? So here's kind of a nifty trick. If you bring this up here and you bring that over there, I could just focus on what the tops are. What's 37 times 15? 555? Nifty, I like it. And what's 31 times 19?
589.
Which is, sorry?
589.
589, I love it. Which way would you write the inequality here? 555 is less than, so that's the same way you write the inequality here. And why does it make sense? Because this top would become 555, this top would become 589 over the same bottom, so obviously this one's bigger than that one. Okay, that's a little bit of a shortcut, right? Okay. If you multiply these and these numbers are the same, then they're equal. Kick ass. Now real quick, why is that sort of silly? Because if they are equal, I should be able to either reduce them or build them up to be the same denominator without having to multiply the things. Are you with me? Okay, okay. Oh, okay. I already did that piece early. All right. So let's do this. And then I'm going to see if I can grab the manipulatives real quick. Okay. We only have one little thing left to do here. For fractions, what's interesting is if you give me any two fractions, do you agree with this statement? Between any two fractions, there's another fraction. What do I mean by that? Can you give me, is it true that between any two whole numbers, there's another whole number? Think about it. If it was 3 and 7, sure. What if it was 3 and 4? Is there another whole number between those? No. But if you give me any two fractions, I'm claiming that I can always find a fraction between them. Do you guys agree with me? Okay, so there's a couple different ways you can do it. So if I just take 1/4 and 1/3. So let me just throw it at you. Think about this for a minute. Can you come up with a method to find a fraction that is between those two? Think about it. Don't say anything, just think about it. Some methods are a lot more disgusting. So what do you guys think? If the fractions I gave you were these, why is that easy? What fraction is between those? Freaking 6/12, right? So what do I do with this then? One way to do this is to make 1/4 become 3/12, and then 1/3 would be 4/12. Now, 3 and 4, nothing between those, correct? So just keep going. This would be how many 24s? 6, and this would be how many 24s? Now I can see what's between them. 7 24s. Are you with me? Kick ass. Is that all right? Okay. You could also, let me ask you this. If I give you any two numbers, can you always find the number that's right in the middle of them? So for example, if I give you 10 and 34, can you quickly find out what the number is right in the middle of them? How would you do it?
You would add them together and divide them.
Exactly. So if you take the average of any two numbers, you get the number that's right in the middle of the two. This is the method that with fractions is more disgusting. So I'd have to add these and then divide that by 2, right? That seems a little more daunting. But we basically did the work already, right? 3/12 plus 4/12, 7/12. Now does anyone know how to do that? 7/12 divided by 2?
Times 1/2.
11, which kind of opens up the next thing I want to do. Let me say this a few different ways. What is 7 being divided by? What is 7 being divided by? 12, and it's being divided by 2. So overall, it's being divided by 24. Do you guys see that? That's one way to kind of look at it very directly, right? Now, okay. So I'm going to kind of, if I give you two fractions, the most concrete way to find the number in the middle is to just build it up until there is room in the middle to find a number, right? You just keep building it until you find it. Or you could do that. You could add them, divide by 2, which is a little more computationally gross, right? I want to talk about how we do problems like this just for a minute. Wouldn't this be 7/12 divided by 2? And I think you all have this memorized, but I don't know how many of you guys know why this is true. When I divide fractions, what do?
Change the
Multiply by the
reciprocal.
reciprocal. I love it. Yeah. we kind of know this. You guys know this. If I cut something, if I divide something by 2, that's the same thing as cutting it in half. That's exactly what these two statements say. Divide it by 2, cut it in half, right? So either way, you get 7/24, which is the answer we got earlier. Yay. Yeah, like it. Let me make sure there was nothing else. Yeah. Oh, okay, that's right. So real quick, if I had 4/9 divided by 2/3, I'm not going to show you the way to do it. I'm going to show you why the way we do it works. Do you understand? Whenever I show students this, they look at me and they go, my God, Jeff, what are you doing? Why are you making this so hard? Right? I can see that in their eyes. That's what they want to do to me. I want to explain to you why we multiply by the triple. Does anyone know why we do that? Okay. Is anyone curious even this much to know why we do that? And you're all like, just show it to me, man. Okay. Again, what did I say? You're never going to do what I'm about to do, because what I'm about to do explains why what we do works. You're never going to do what I'm about to do, unless you're explaining it to somebody else. Couldn't I write this like this? Do those mean the same thing? That looks much worse. This is where students look at me like, what are you supposed to help, Jeff? What have you done? Why does that suck? Why does that suck? Just tell me, why does this suck? Why does this suck? You got fracception, right? You got fractions inside of fractions, right? Okay. Here's another way to say why this sucks. The bottom is not 1. Isn't 1 the best denominator to have? Would you agree with me? 1 is one's awesome. What do I, and also with fractions, we said this earlier, I'm allowed to multiply the top and bottom by any damn thing I want to except 0, right? I can multiply the top and bottom of any fraction by 11.2 if I wanted to, and it'd be fine. Y'all with me? So, what would I multiply this by to make it become 1, which is the best freaking denominator ever? What do I multiply a fraction by to make it become 1? Do you guys know? It's reciprocal. Beautiful, right? So if I multiply by 3/2, I have to do it to the top also, right? So this becomes 1. So this equals this. So then we just made a shortcut out of that, thank the gods. We're not going to force students to write, complex fractions. No, we just made a shortcut out of it. Now to do this, you just multiply by the reciprocal. Now, just because I'm going here, would I just go ahead and make that 12/18, or is there a slightly better thing to do right now? Who remembers? What's a better thing to do? I don't want to make my numbers get big when I'm going to have to reduce eventually anyway. Why don't I just reduce right now, right? 2 goes into 4, 3 goes into 9, 2/3. Shabong. And the answer makes sense, of course, because 4/9 divided by 2/3 should be the number that when I multiply by 2/3, I get 4/9. And 2/3, so 2/3 is 4. I lock it. Notice one thing you have to be careful about. What's 4 divided by 2? 2. And what's 9 divided by 3? 3. So you could sort of just divide straight across. The reason that gets a little gross is, what if something doesn't divide evenly? How do you take care of that, right? So you got to be really careful if a student starts doing that. You're like, okay, that's a good observation to make, but you got to be careful. It's not always going to be that nice. Okay. Yeah, let me see. I want to at least show you some of these manipulatives. So here's what these are going to look like. Well, let me grab them. I'll just put them over the overhead. let's see. So what we got here, something like that there, let me see, maybe. We got this here. We got this here. We got this here. Choo. So we got those pieces, parts. So it doesn't take too much to see. Now, if I would have been able to get in this room earlier, I would have had all this put together for you guys, but actually, let me see. How many bags? There's a few. Okay, let's do this. Okay, few. Looks like it's still, oh, sweet. Okay, few. Can you guys just grab one other person, don't grab them, but just motion to somebody else that you want to pair up with them? Can you just pair up real quick? Okay. And I'm gonna pass some of these out. Whoa, that's a lot. Oh, I really wanna see how many people have 2, 4, 6, 8, 10, 12, 14.
I'll find someone.
So maybe you have one group of 3. Yeah. Just don't have enough little bag juice. Let's say I never gave me anything. Just so you know, we do, after every use, we do wipe these bags down, we do wipe the parts down. I mean, you could be with, a group, you can make a group of 3. So I don't know, you wanna be with these guys? Or whatever you like, yeah?
Honestly, anyone's fine. Like, I don't mind.
Huh?
Are you guys
Okay.
you guys are good.
Alright, so, let's see. The fact that 2 reds make this, right, obviously means that each one of those represents half. Okay, hold on. You guys are on. Do they want me to say? Yes, I want you to say. Is this the piece I wanted? Yes, okay, I love it. Now, this little blue dude, take a minute, figure out about anything about the little blue dude. Don't say anything. So what do you guys think is, what do you think is true about the blue dude? 1/3 all of it, kick ass. And of course the green dude. Alright. So this is sort of like what I was saying earlier about 3 distinct pieces together make a full piece. So they would each be 1/3 of a full piece. The little triangle dudes are like little pieces of pizza. Oh, different kind of green. Okay, that works. So, how would you illustrate 1/2 times 1/3 with these pieces? How would you illustrate 1/2 times or of 1/3? Which piece is the 1/3 piece? The blue dude, right? Which piece do you get if you cut that in half? The green dude. Okay, good. And so let's identify the parts again. Green is 1/6, blue is 1/3, red is 1/2. Of course, this dude is 1. So if I take 1/2 of 1/3, sure enough, I get 1/6, right? Is that cool? And this is related to something, I think I've said this before, but every now and again I'll get a little something that I see in my students that I get worried about what's happening in high school. Because for example, I think I told you guys this, the word of, not everybody comes out understanding what that word means, right? So if every crate has 3 apples and I have 4 of them, 4 times 3 is 12. So if I want to do half of a third, that's 1/2 times a third, right? And it used to be like everybody just knew that, but over time I saw that fewer and fewer students just kind of knew that. So 1/2, and why does it make sense? 1/2 times 1/3 would be 1/6, correct? Okay, now think about this. What about, I really should have some paper so I can write this down. That'd be awesome. Here we go. What about love? No, what about 1/6 plus 1/3? So what would happen? So can you start? So I want to point something out. Again, the purpose of manipulatives is to give the students something tactile. It's something they're playing with. But then as a teacher, you try to connect it to some concept, right? So if I were teaching elementary school, I would give the students this. I would kind of make sure they weren't like eating them or whatever, depending on how old they are. And I would just let them just play with them for a while, just to get used to the pieces themselves. Then you start to imbue these with concepts, right? Like the red is 1/2 of the whole thing, whatever. How would you illustrate 1/6 plus 1/3? What would you do? Yeah, take one of the greens and one of the blues, and if you add them together in the right way, you get a red, right? So that would illustrate, of course, the red they know already is 1/2. Now, they could get that answer, and it's fine that they don't understand mathematically why that's true. They can see visually why that's true. And then later, if you go into the math of it, you can remind them what happened with this. Does that make sense? So, of course, the math behind this would be what? How would you add these? 1/6 plus. How would you add this? What would you do? 2/6, right? Got to make it the same denominator. 1/6 plus 2/6 is 3/6, which reduces to 1/2. Kabam. And of course, where's the 3/6? There's the 3/6, right? You guys follow with me? Okay. So there's the 1/3 is 2/6, and then there's the 3/6, and then there's the 1/2. Okay, all kinds of stacking you can do. What about Jeff? What about 1/2 minus 1/6? Now you start to feel the connection with the blocks, the flats, the longs, and the units. So you plop down there 1/2, and then what do you have to do immediately? If you want to take away 1/6 from this, I'm not going to give them all like a little knife. All right, kids? No, probably not good. So I'm going to take this sucker end. How would I take 1/6? Which piece represents 1/6? Green dude. How can I take one of these away from him? Well, the first thing I could do what to him? So can I do this? This is the same thing, yes? Right. So this is 1/2. Jeff, you do it, buddy. So, real quick, if I was trying to subtract using base 10 blocks, base 10 flats and longs, and I have to borrow, physically that's just taking like a long and breaking it up into 10 parts, and then I can take those over, correct? The exact same damn thing happens here, right? I'm gonna break one of the bigger pieces up into the smaller one, so then I can take parts of those away, the exact same way. So there's a lot of analogies between this and working with the base 10 pieces. So now I can just visually do this. Whee! Right. So now they can count. Well, that's 1/6, 2/6. which course is 1/3. I like it. And of course, I'm almost certain some of you guys realized if 1/6 plus 1/3 is 1/2, therefore 1/2 minus 1/6 must be 1/3, the other piece, right? Okay, I like it, I like it. Now, what about if I do this? What about 5/6 plus 2/3? So take a minute and try to figure out what that is. You're gonna need to take out some more parts. You got a whole bunch of parts. You need to take some more out, right? So represent 5/6. I think everybody has enough pieces, right? Oh, you don't? I'm sorry. Oh, you only have a few? Oh, shit, of course. I was being hopeful about how, let's see, let me give y'all another bag. Yeah, these are not really divvied up too well, are they? Oh, this has got a bunch of green. All right. So Neva, oh, you got even between you. Oh, between everybody in the group, can you get enough green pieces for this? Oh, good. I like that. Is there enough green in there? Maybe? Are you guys okay with the number of greens? Okay. You guys are good? Yeah, you got enough? Okay. Okay. Do I have enough green pieces? I think I do. You might need even more green pieces, unfortunately.
Oh, you're right.
If you do this in a certain way, we'll see. One way you could do this, that would require you to have more green pieces than this, is to break this one up. But what's another way you could do this? I just want to combine these, right? So I'm sorry, I heard it. I think I heard it. Are you hearing voices, Jeff? Could be. If I take two of these over, right? You guys with me? And so that would be what? 1 and a half. 11. Is that cool? All right, so visually it comes out to be 1 1/2. Or what as an improper fraction? What's the shortcut to do change this back into improper? You guys know?
Denominator times the
Yeah, 2 times 1
plus 1.
plus 1, yeah. So 3/2. So let's actually do the math. Let's see, that's what we got visually. Let's do the math. So how would the math work on this? What would you have to do? 5/6 plus 4/6. 9/6. So this is where, if you want to show them, what would this mean visually? What would I need to be able to do to actually capture this math, but with the manipulatives? Let me give myself all the parts again. Okay, got too many. No, that's enough. 5/6 there, 2/3 here. How would I represent 4/6? What would I? God, that angle's really weird. You got a little tiny finger. 4/6. What would I have to do to kind of show where 4/6 comes from? What would this mean? How many? I would need four whats? 4 greens. And that would just mean I would take each blue and break it up into whatever. Come here. Break it up into greens. So then I've got 4/6, right? So you can actually show the math along with the visual. Now, here's what's really weird though. We didn't do it that way. We did it like this. So this might be a bit much, but let me see what you guys think. What the shit would that look like? That thing, right? Just take this put it here. What the hell would that be mathematically? And you're like, I don't know, dude. So help me out. This piece right there. What is that? That's a third, right? That's like a blue. That's a third. So aren't we taking 1/3 away from this and giving it to this? Does anyone remember that process, what it's called? To take something from one number and give it to the other number. When I'm multiplying or adding them. Compensation. I was going to take my wallet out. I got no money in it, so it wouldn't do any good. You guys kind of with me? Now, I could tell, if you really think about it, you are not excited to look at the math of this. You guys understand what this means? What did I just take away from 5/6? I just took away 1/3, but really I just took away 2/6, right? So what I really did mathematically, I want to make sure you guys are all cool with the visual, yes? The visual kicks so much ass, because you're just sort of like making one complete piece, and then you can count how many leftovers you got. That's beautiful, it's not difficult. But what would the math look like? Well, the math would look like this. I took 5/6 and I took 2/6 away, so then I gave 2/6 to the 4/6. And then you can see how that's 3/6 plus 6/6, and that sure enough, that's 1.5. Is that cool? So the ideas of compensation and compatible numbers and all that kind of stuff, they carry over to fractions the same way. I like it. What about this? What about, how would you represent, for a student, 3 times 1/6? This one's pretty quick. I wrote it specifically this way for a reason. What does 3 times something mean? Remember 3 times 2. How did we show that? We would write 3 groups of 2s, right? So here I want 3 groups of 1/6. So there's 1 group, 2 groups, 3 groups. Is that cool? And what does that make, of course? 1/2. And again, the student just knows the shape corresponds to a name. This shape is 1/2. This shape is the red, and that's the 1/2 piece, right? So a lot of this could be purely tactile, purely naming things, and not even mathematical yet. Okay. So finally, what about this? How would I do? I want to do that side. You and paper, me and paper, the whole time. What about if I want to do, what do you got, Jeff? 1/2 divided by 3. I'll give you a moment to think about it. You guys can talk to each other. There we go. So it kind of makes sense. You would start with the 1/2 piece. It makes sense. I can only, the easiest way to divide something in thirds. Sorry, I'm laughing near you, not at you. The only thing the easiest way to divide something in thirds is if it's already in groups of 3, correct? So let's just make this into groups of 3, and I think I saw a lot of you guys putting these pieces on top. So now it's a group of 3, right? So if I cut it in thirds, then that would be this, and what's that? 1/6. Now real quick, help me out. What is 12 divided by 3? Why? I love the look I get from you guys, you're like, because, dude. Because 3 4s make 12, correct? So whenever I divide, one of the easiest ways to look at it is how many of the denominator does it take to make the numerator? So 12 divided by 4 is 3, because it takes 3 4s to make 12. So 1/2 divided by 3 is 1/6, because it takes 3 1/6 to make a half. What is 1/6 plus 1/6 plus 1/6? Which is 1/2. It's crazy. And again, I'm not saying you guys don't know this. I'm just saying with these pieces, how can you connect it to the mathematical idea, right? Okay. What was what was the other one I wanted to do? Oh, I don't know where those are. We have incomplete parts. We have a part like this that doesn't really, I think that works. What was the part? Anyway, we got smaller pieces that get very exciting because then they end up all over the room. But I think, let's do this. I have a big old meeting coming up and I'd love to have more time to get ready for it. So let's call it a day. Is that all right? You guys look very excited about it. Do me a really good favor. Make sure you get all those pieces back in the bag. You're gonna have to come back and wipe these things down. Thank you, yes. Oh, yeah. At least I can. If anybody didn't get their updated grade sheet, let me know. Or if you didn't get your test